Welcome to this coding problem walkthrough. Today, we'll be exploring LeetCode problem number 1083. While the exact title and details of this problem are unavailable, our focus will be on outlining a general approach to solving similar design problems. Let's dive in. It seems that the specific data for LeetCode problem number 1083, titled "Cannot retrieve exact data for this problem," is not available. This placeholder indicates that the problem details are inaccessible. Unfortunately, without the problem statement, examples, or constraints, we are unable to provide a detailed walkthrough or explanation. If you encounter this issue on LeetCode, it is recommended to check the forums or contact their support for clarification. Thank you for your understanding. When approaching a coding problem with limited details, it's helpful to start with a structured methodology that explores multiple paradigms. One common starting point is the brute force approach. This method is intuitive because it involves systematically testing all possible combinations or paths to find the solution. While it's simple to implement, brute force solutions are often inefficient for larger input sizes due to their high time complexity, which can be n squared or worse. However, for smaller datasets or problems with loose constraints, brute force can be a practical first step. Another powerful paradigm is the divide and conquer or recursive approach. This involves breaking the problem into smaller, more manageable subproblems, solving them independently, and combining their results. This method is particularly effective for problems that exhibit overlapping subproblems, and with the help of memoization, it can significantly reduce redundant computations. It's a strategy that balances problem decomposition with optimization opportunities. While divide and conquer is often more efficient than brute force, recursion can introduce challenges such as stack overflow in cases of deeply nested calls, unless tail recursion optimization is applied. Another strategy to consider is the greedy algorithm. This approach works by making locally optimal choices at each step, under the assumption that these choices will lead to a globally optimal solution. Greedy algorithms are particularly suited to problems involving intervals, sorting, or certain pathfinding tasks. They are efficient, with time complexities often around n, or n log n. However, they are not universally applicable and may fail in scenarios where backtracking or exploring all possible paths is required. Dynamic programming, or DP, is another valuable technique. It's a natural choice for problems with overlapping subproblems and optimal substructure, as it avoids redundant calculations by storing the results of subproblems in memory. DP is highly efficient for many optimization tasks, often reducing complexity to n, or n squared, but it can be memory intensive. Lastly, leveraging advanced data structures like heaps, segment trees, or hash maps can further optimize complex problems. Selecting the right data structure can dramatically improve efficiency, though it may come with added implementation complexity and space requirements. The chosen strategy for solving a problem, especially when its details are unclear, often starts with exploratory coding. Beginning with a brute force approach allows us to understand the problem's mechanics and identify key constraints. From there, the solution can evolve based on the insights gained. For example, if patterns of overlapping subproblems emerge, dynamic programming might be appropriate. If the problem involves making optimal choices at each step, a greedy algorithm could be effective. Alternatively, certain constraints might point to the use of custom data structures for optimization. The iterative approach of starting simple and gradually refining the solution ensures clarity and correctness at each stage. The key here is to avoid premature optimization, which can lead to inefficiencies or errors. The aha moment often comes when recognizing specific patterns or constraints that simplify the problem, such as identifying recursive relationships or opportunities for state transitions in DP. This phased strategy not only builds a solid understanding of the problem but also ensures that the final solution is both efficient and robust, tailored to the input size and edge cases identified during exploration. To begin solving any algorithmic problem, the first step is to fully understand the problem statement. This means carefully reading the description to identify key elements such as the input constraints, the required output, and any edge cases that could arise. For example, are there scenarios where the input is empty or unusually large? What exactly are we trying to achieve? Are we searching, counting, or optimizing? Once the objective is clear, the next step is to break down the problem into manageable components. If it involves structures like arrays, matrices, or graphs, think about their dimensions and the operations typically required, like sorting or traversal. For optimization problems, consider if established techniques like greedy algorithms, dynamic programming, or divide and conquer are applicable. Also, check if the problem can be reduced to a well-known one, such as two-sum, binary search, or finding the shortest path. Finally, selecting the right data structure is crucial. Arrays are great for sequential data, while hash maps excel at fast lookups. For dynamic ordering tasks, heaps or priority queues are the better choice. If the problem involves relationships or connections, graphs and their representations, such as adjacency lists or matrices, will be key to a solution. Once the problem is understood and broken down, the next step is designing the algorithm. It's often helpful to start with a brute force approach to ensure correctness. This means writing simple code that systematically checks all possible combinations or permutations. While brute force is rarely efficient, it helps identify potential bottlenecks and understand the problem deeply. From there, you can use established patterns or optimizations to refine the solution. For instance, sliding window techniques are invaluable for subarray problems, binary search is perfect for sorted data, and dynamic programming works well for challenges involving overlapping subproblems. After designing the approach, it's time to implement the core logic step by step. Break the algorithm into smaller components and write helper functions to handle repetitive tasks, such as depth-first search or binary search. Clear and meaningful variable names make the code readable and maintainable. Once the implementation is complete, rigorous testing on edge cases is essential. Consider a variety of inputs, like small arrays, large arrays, empty data, or special values such as zeros and negatives. This ensures the algorithm adheres to all constraints and handles unexpected scenarios gracefully. After testing, the next focus is optimizing the solution. This involves refining the code to eliminate redundant operations and verifying if other data structures might improve efficiency. For example, replacing a list with a hash map could speed up lookups. Carefully analyze the time and space complexity to ensure the solution meets the problem's constraints. Mastering algorithm design also requires recognizing common patterns. Many problems, such as those involving sliding windows or dynamic programming, follow established approaches that can save time when applied correctly. Another key insight is the importance of edge case handling. Even well thought out solutions can fail if they don't account for edge cases, making thorough testing critical. Finally, it's important to balance trade-offs. Sometimes optimizing time complexity increases space usage, and understanding which constraint is more critical can guide better decisions. Remember, algorithm development is an iterative process. Starting with a brute force solution and incrementally optimizing it is a natural and effective approach. A deep understanding of data structures and their operations is essential for solving algorithmic problems effectively. Arrays, for instance, are ideal for sequential data and offer constant time access but can be inefficient for insertions and deletions. Hash maps, on the other hand, provide average O(1) time complexity for lookups, making them perfect for tasks like counting frequencies or storing indices, though they require additional memory. Heaps are particularly useful for dynamic ordering problems, such as finding the kth largest element, with operations like insertion and removal taking log n time. Graphs are a versatile choice for modeling connections or relationships. Sparse graphs benefit from adjacency lists, while dense graphs are better represented with adjacency matrices. Key operations also play a major role in algorithms. Sorting is often used as a pre-processing step to make other operations more efficient. Binary search is invaluable for quickly finding elements in sorted data, reducing time complexity to log n. For graph-related challenges, depth-first search and breadth-first search are essential for exploring connected components or finding paths. Finally, dynamic programming is a powerful technique that transforms exponential time problems into polynomial time solutions by reusing intermediate results. To illustrate these concepts, let's walk through a classic example problem. Suppose we're given an array of integers and a target sum, and our goal is to find two numbers in the array that add up to the target. A highly efficient approach involves using a hash map to store complement values. As we traverse the array, for each number, we check if its complement, the value that would sum to the target, already exists in the hash map. If it does, we return the indices of the current number and the complement. Otherwise, we store the current number in the hash map and continue. This approach has a time complexity of O(n), since we make a single pass through the array, and a space complexity of O(n) for the hash map. Testing the solution against edge cases is crucial. For example, an empty array or an array with only one element should return no result. If there are multiple valid pairs, the algorithm should return any one of them. For large inputs, the efficiency of this approach ensures it performs well within constraints. By applying such systematic steps, challenging problems become approachable and solvable. Since the problem description for LeetCode number 1083 is unavailable, the implementation cannot proceed without understanding the requirements, constraints, inputs, and outputs. The provided template includes a generic solve method within a solution class, which is the standard structure for LeetCode problems. Once the problem details are clarified, this template can be extended to handle specific logic, such as iterating over inputs, applying algorithms, e.g., sorting, dynamic programming, recursion, and returning results. Example usage comments are included to demonstrate how the solution would be executed with appropriate inputs. This is the Java implementation of the placeholder logic provided in Python for the unspecified problem. The class structure mirrors the Python solution, with a method solve that accepts a variable number of arguments, object, args, to accommodate any input types. Java-specific features like the use of the main method for execution and explicit type declarations are included. This template can be expanded once the exact problem details are known. Here, we start with a placeholder example of the solve method being called without any inputs. Since no data is provided, the args parameter in the method is empty. When the function runs, it simply executes the pass statement, meaning no operations or changes occur. As a result, the method returns none. This example highlights the initial behavior of the method when there's no input and no logic is implemented. It effectively does nothing and provides no output. Next, we examine a generic case where mock inputs are passed to the solve method. In this example, the tuple 1, 2, 3 is provided as the args parameter. Again, the method executes but contains only the pass statement, so no operations are performed on the input data. Consequently, the solve method does not process the inputs and simply returns none. This demonstrates that even with inputs, the absence of logic means the method remains non-functional. Now, we consider a hypothetical scenario where the solve method might include problem-specific logic. The input consists of a list of strings, apple, banana, cherry, and a target string, banana. The hypothetical logic iterates through the list and compares each element to the target. For the first element, apple, there's no match. For the second element, banana, a match is found. The third element, cherry, is also not a match. This step demonstrates how the method could potentially analyze and evaluate the input data. Finally, in the second step of this hypothetical scenario, the method would return the index of the matching element, which is 1. This indicates that the target string banana was found at position 1 in the list. The output reflects how the method might behave if logic were implemented to solve a specific problem. While we don't know the exact requirements of the problem, this example gives us a sense of how the method could process inputs and return meaningful results based on a defined purpose. When analyzing time complexity, our goal is to determine how the runtime of an algorithm scales with the size of the input. For iterative operations, such as traversing an array of size n, the time complexity is typically O(n). If you have nested loops, the complexity increases multiplicatively, like O(n squared), for 2 nested iterations. For recursive operations, the time complexity depends on the depth of the recursion and the number of calls made at each level. For example, a binary tree traversal has O(n) complexity because each node is visited exactly once. Sorting algorithms introduce another layer of complexity, often O(n log n), as seen in algorithms like quicksort or mergesort. To calculate the overall time complexity, we sum up the contributions of each part of the algorithm. For instance, if the algorithm reads input in O(n) and sorts in O(n log n, the total time complexity becomes O(n log n), as this is the dominant term. Space complexity focuses on how much extra memory an algorithm requires as a function of the input size. Auxiliary space is one key factor, as it accounts for any temporary storage used during the computation, such as recursion stacks or hash maps. For example, if you use a hash map to store frequencies, it requires k space, where k is the number of unique keys. Input size itself also impacts memory usage, and for an input like an array of size n, the space cost is n. Recursive algorithms, in particular, can incur additional space costs due to the recursion stack, which depends on the depth of recursion, denoted as d. By breaking down memory usage into these components, we can better understand the overall space efficiency of an algorithm. When comparing brute force and optimized approaches, the difference often lies in how they handle time and space trade-offs. Brute force methods tend to have higher time complexity because they perform many unnecessary computations. For example, checking all pairs in an array has a time complexity of n squared. Optimized approaches, like sorting followed by a linear pass, can significantly reduce this to n log n, or n in some cases. On the other hand, brute force techniques might use less memory since they avoid additional data structures, but this comes at the expense of runtime efficiency. Optimized solutions often strike a balance, using extra space to achieve faster runtimes. Best, average, and worst-case analyses help us understand how an algorithm performs under different conditions. The best-case scenario happens when the input is structured in a way that minimizes operations, allowing the algorithm to terminate early or run more efficiently. The average case calculates the expected runtime over all possible inputs, making it the most practical metric for real-world applications. Meanwhile, the worst-case scenario represents the most challenging input, where the maximum number of operations is required. This is useful for understanding the upper limit of an algorithm's runtime. While we can't determine exact values without specific problem details, the process involves analyzing how the algorithm behaves under each of these conditions to derive its complexity. One of the most common mistakes when tackling coding problems is misunderstanding the problem statement. Skipping the description or not fully clarifying the constraints and edge cases can lead to solutions that fail for scenarios like empty arrays or negative numbers. It's critical to take the time up front to understand these details. Another frequent pitfall is relying on inefficient solutions. For example, using a brute force approach for a sorting problem might work for small inputs but can exceed time limits for larger datasets, especially if the complexity is n squared, instead of n log n. Additionally, overlooking edge cases such as single-element inputs, duplicates, or extreme values can cause runtime errors during execution. Lastly, choosing the wrong data structure for the task can significantly impact performance. For instance, using an array to track frequencies may lead to unnecessary nested loops, whereas a hash map could accomplish the same task more efficiently. Being mindful of these mistakes can save time and frustration in the long run. Another frequent issue is off-by-one errors, which can arise when managing indexes during loops or recursion. These occur when you start at the wrong index, overshoot array bounds, or miscalculate conditions in zero-based indexing. Paying close attention to the boundaries of your loops can help avoid these errors. Now, when it comes to interviews, recognizing common problem-solving patterns is a crucial skill. Techniques like sliding windows, binary search, or dynamic programming often appear repeatedly. Identifying these patterns early allows you to approach the problem more systematically. Additionally, interviewers often value solutions that balance time and space complexity. For instance, reducing memory usage with an O1 space solution might be prioritized over marginal runtime improvements. It's also important to explain your thought process clearly before jumping into the code. Demonstrating correctness should come first, with optimization as a secondary step. Finally, strong debugging skills are essential. Always be ready to walk through your code with sample inputs to identify and resolve issues during the interview. To deepen your understanding, there are several related problems worth exploring. For example, LeetCode 121, Best Time to Buy and Sell Stock, is an excellent introduction to greedy algorithms. LeetCode 53, Maximum Subarray, showcases Cadon's algorithm, a fundamental dynamic programming technique. LeetCode 621, Task Scheduler, is a great way to practice prioritization and greedy methods, and LeetCode 198, House Robber, is a classic dynamic programming problem that deals with overlapping subproblems. Now, when considering how to approach problems, there are trade-offs to keep in mind. Brute force methods are straightforward to implement and work well for small inputs, but they quickly become inefficient as the input size grows. On the other hand, optimized algorithms, like those using divide and conquer or memoization, are much faster for larger inputs but require a deeper understanding of algorithmic techniques. Lastly, space optimization is a powerful strategy for reducing memory usage in resource-constrained environments, though it may add complexity or make the implementation harder to follow. Being aware of these trade-offs can help you choose the best approach for the problem at hand. Thanks for following along. In this session, we reviewed a general approach to handling design problems when details are unclear. Remember, adaptability and solid fundamentals are key. Don't forget to like and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!